Hello, everyone. This is Shakil, and I hope all will be doing well. Well, here I am with the part two of this very important video about May 2024 AQA International AS Physics Unit 1. So, in the previous video, we looked upon a very long section 1, and you know that section 1 contains 8 to 9 questions. So there was 8 questions in section 8. This was a long section, but the section B is pretty much simple one. It's having just 2 questions, and basically section B is the graphical analysis. So this is graphical analysis part of your AQA exam. So you have to look for the technical terms related to graph. Let's say you have to find the gradient, and they can ask you to plot the error bars. And then through the error bars, you could be asked to find the absolute uncertainty in gradient or absolute uncertainty in y-intercept, or you can be asked to plot the graph as well. And then the last thing is you can compare the given equation with y is equal to mx plus c to look for finding some of the important quantities from the question. Okay, so these are the main things. Now let's jump into the question now straight away. If you read the question, reading question is very important. Figure 11 shows the variation of stress with strain for a type of steel. That made your mind that you're going to study something about steel, and it's a stress strain graph. Whenever the graph is there, the first step is always reading the scale values very carefully and highlighting any prefix or power of 10, which is here, 10 raised power 6. You have to be careful with that, because whenever you use y-axis value, this 10 to the power 6 will be part of that value. The next is strain. You know the strain is having no unit, so that is easy going. If you look, oh, sorry, that's a big jump. If you look at the question, they're asking you that you have to show that the Young modulus of the graph is approximately 200 gigapascal. Whenever they ask you that you have to show, this is considered as usually the easier part, and it is 1 mark as well. Now you have to use your knowledge. So what is your knowledge about this graph? The knowledge is that the Young modulus, which we denote with E, comes from gradient of the graph. Why? Because it is equal to stress over strain. And stress over strain is what? It is gradient of this graph. So all you need to do is to carefully look for the gradient. Sorry. Okay, now looking for the gradient, let me just highlight it so that you can easily view this. As far as the gradient is concerned, okay. So now let me look for the point. You have to look for 2 points. Obviously, the graph is starting from origin, so my first point is 0, 0. And the second point could be the last point, or it can be anywhere else as well. So what you say? If I take the last point, okay, I can do that. So let's look for the last point now. So you know that gradient is y2 minus y1 over x2 minus x1. So the y2 is the last point, which seems to be, well, I have a minor eyesight problem, but this is 1, 2, and 3. This is little above 3, but we can say this is 3. And from here, if you look at the values, 5 big squares representing 200. So it means that one small square will be representing 40. So it means that 1200, 1240, 1280, and 1320. So this is 1320. So you say 1320, but don't forget to include this 10 to the power 6 over there. So 10 raised to the power 6. Y1 is 0, so just forget that. And over here, it is 0.007 and then 0. So you got your gradient. So this is the way to look for the gradient. And let's say you have solved that like 13.2 into 10 raised to power 6 minus 0 over 0.007 minus 0. And let's say your answer is not 200. Your answer is just closer to that. Well, like for example, over here, if we look at its value, let me just open the calculator. So the value here is 13.2 and then divided by 0.007. So the answer is, my answer is 1885.7. 1885.7 and then into 10 power 6. But now I will look upon 1.885 into 10 raised to power 9. And then I look for this 9 is actually giga. This is giga. So I will say, yeah, just hold on for a second. Okay, I sorted out the problem. Actually, this was not 13.2, but this was 1320, right? 1320. And when you do that, 1320, then your answer is slightly different. Your answer is not this. Okay, so what you do is when you have to divide these two. Okay, so your answer is this. And then what you do is you just have to use the calculator. Just use the calculator. And we know that this decimal is at the end. So 1 and 2 and 3. So you moved 3 places over there. So you add 3 over there. This is the manual way to solve it. And then 188.571 into 10 raised to power 9. And you know the 10 raised to power 9 is giga actually. So you say that it is 188.571 gigapascal. You will write this and then you will say that we can round this off to 200 gigapascal. So this is actually the legal way to solve this question. Okay, let's move on to the next part. There is a steel cable that is attached to the wall using the device called a turnbuckle. This is a turnbuckle. The other end of the cable is also fixed. Okay, so this is the cable, the main cable, which is attached with screw with this central body. And then this is attached, the other part is attached to the rigid wall. So this central body or the turnbuckle is actually used to tighten this cable. So when you rotate the turnbuckle, then these two screws will get closer to each other and then the tension in the rope is going to be increased or the rope is going to be stretched. That's how it works actually. Okay, so they've explained that the turnbuckle is used to adjust the tension in cable as the central body is rotated. The separation of the screw changes. The change depends on the direction of the rotation and the amount of rotation of the central body. You can turn it clockwise or anti-clockwise to increase or decrease the tension. Now they're saying state and explain what must be done to the turnbuckle to increase the tension in the cable. Increase. So you will say that turn it such that two screws get closer to each other. Get closer to each other. That's it. As they're saying 1 mark, so it's enough that you should be turning it such that the two screws will be getting closer. You can see that if this screw gets here, this gets here, obviously the rope is being stretched. And the opposite to it is if you want to lose that, so you have to move it in the other way so that the screws move away apart. That's how the tension is going to be decreased. Okay. The next thing, this question is a bit tricky and involves a new concept. This was never tested before in AQA A-level physics. So let's look upon that. The thing is, the figure shows a section of screw from the turnbuckle with one complete rotation of the central body. Both screws move through a distance of 1 pitch relative to the central body. Okay, so when it means that, they're saying when the both screws move through a distance of 1 pitch, both screws, the important is both screws move. So distance of one pitch relative to the central body. So this is the diameter of that screw, and this is the pitch, which is actually the distance between these two slots. So what we can say is both screws have the same diameter and same pitch. The diameter of the screw is this. So this is 14 millimeter, or we can say 1.4 centimeter, whatever. For one complete rotation of the central body, the extension of the cable is 1.3. Okay, so it means that when you rotate the central body for one complete rotation, the extension is this. This is the total extension. So what is the ratio of diameter to the pitch? Okay, now look. The thing is that extension is in the cable, right? And over there, they were saying that when you rotate the turn body completely, both the screws, then a one pitch distance is moved. It means that the rope is attached to only one side of this. It means the extension, the extension in the rope will be half of that what they have told us. Like they have told us that the that the extension is 1.3, but the problem is this 1.3 sorry will be due to the pitch. So we say here that if they, I don't know why it is jumping today. Okay, anyways, the diameter is 14 millimeter. And one trick here is that this is in millimeter and what, oh, well, this is also in millimeter, so it's not a trick. But the only trick is that this pitch should be the half of the extension. Why? Because when they have rotated it once, there are two screws. So the one screw will be moving half of this. So that is why we say this is the pitch. So actually, pitch is equal to extension over 2, or we can say 2 into pitch is equal to extension in the cable. So that's why we divide this extension with 2 to get the pitch. So this was the only thing over here. So 14 over 0.65, since millimeter canceled away, and you get an answer. So now one important thing here is that how you should be writing this answer. Whenever they say that write in ratio, don't write in your answer in ratio. This is 21.5. So you have to write your answer as 21.5. Never write your answer in this fraction, because then you will lose, possibly you can lose your mark. Okay, now let's move forward. They're saying that the cable is initially under the tension with a stress of 201 megapascal. So this is the initial stress. The unstretched length is this. They told you this is the unstretched length. Now they're saying determine, okay, find using figure. So this is a big hint for you that you have to use that figure. And this figure is actually graph the initial strain in the cable. So what is the initial strain in the cable when the stress is, here they have used the word initially under stress. So initial stress is 210 and you have to find initial strain. So just jump back to the graph and look, it's just a scale reading thing. You just have to read the scale that what is the value of the strain at 210. So just look upon that. So we can see from here that each small square value is 40. So after 200, it is 240. But where should be 210? I have to like zoom in so that you can easily view it. So this is 200 and this is 240. So of course, 210 would be somewhere here. So just go over there and you can see that this value is coming out to be here at the first reading. So what is this first reading? If you look for the x-axis small square value, the one small square value is equal to 0.0001, right? Because you divided this with 10. So it means that this is 0.0011. So this is the value at corresponding, and this is also the strain then. So you simply will read the scale value, no need to find, no need to use any formula. Why? Because they have asked you this. This is the problem with this question, that many of you can go for some rigorous calculation using Young modulus or other thing as well. You can do that as well. I mean, but this is the first graph. The first method is just the graph reading. So from the graph reading, you can say that it was 0.0011. So this is straight away your answer. The other method is, the second method is Young modulus method. I mean, you can try that as well. Young modulus is stress over strain. And as you have to find strain, so strain would be stress over Young modulus. And then you can say, okay, my strain is equal to, stress is 210 mega. So be careful that mega is 10 raised power 6. And then you have to look for the Young modulus. And Young modulus you have already calculated over there. It was how much? It was around 200 gigapascal. So 200 into 10 raised power 9. You can use 200 or you can use 18, whatever come, 188. You can use both of them and you can get your answer. So these are the two ways. I will prefer graph reading because that is simple. You simply read and you simply tell the answer. The next one is, the central body is now turned through 8 complete rotations. Now the central body is rotated 8 times. So calculate the new strain in the cable. So you have to tell what is the new strain in the cable. Okay, for this question, you have to understand a thing, that first you have to find that how much is actually the additional strain. So you have to find the additional strain over here that is produced due to 8 rotations. Okay, so we can say that strain is equal to delta L by L, right? And original length, they told you it was 1.8 meters. And for the strain, 8 into 1.3, because for one rotation, the total extension was 1.3. So you just multiply them. So it is 10.4. And it was 10.4 millimeter. Just let me check, double check that. Millimeter, yeah. It was millimeter. So you have to convert that into meters. So minus 3 over 1.8, because both should be in same units. And then what you'll be going to do is you're going to divide them, right? So you're going to divide 10.4 with 1.8 and you get 5.777. Okay, 5.777 into 10 raised power minus 3. So that gives you 0.0058. You can write that as well. So this is your strain which is produced due to 8 rotations. So now you have to look for the previous strain as well, because this was under previous strain as well. So as they are saying new strain in the cable, so we say the new strain is equal to the previous strain plus strain due to 8 rotations. Because they're saying what is the complete strain. So the previous strain was 0.0011 and the new strain is 0.0058. You simply add them. So this is 0.0069. So this is your new strain, right? This was also a tricky part. Why? Because most of the people just can stop working over here. They thought that this is, but then you have to carefully read the question. They said calculate the new strain. So the previous strain was also there and you are doing on top of that. So that's why you have to tell the total strain. So you are going to add that. Okay. The next thing is the cross-sectional area in the cable is this. You have to calculate the new tension in the cable. Now with this strain, what is the new tension? Tension mean force. Force or tension, both are actually same things. So this part is ECF. If you come up with some wrong answer, like if your answer is 0.0058, you use that in the part 6 and you use it correctly, so you will get full marks for that. So as the cross-sectional area is given, so we say that area is given and then the strain is given and you know the Young modulus as well, and you have to find the force. So you will say, okay, I am going to use the Young modulus formula, which is stress over strain. So in this part, what you will be doing is you will be using the strain's value, right? So whatever your value of strain was coming, you have to use that, right? Okay. So okay. So from here, I can say stress is equal to Young modulus into strain. Young modulus, whatever is coming, you have to use that. Not 200, but whatever was the raw value, you have to use that. It was, I guess, 1.9 into 10 to the power 11, and multiply that with this strain, which is 0.0069. So you will get your answer, right? And then what you do is, this is stress. So stress is force over area, and then you simply multiply area with that as well. 0.0069 multiplied by area, and area is given as this. So you can find the value of the force over there. Okay. Let's jump to the next question, the last question for this section. Um, well, this is again related to spring. A student investigates the friction on the block that slides across the horizontal surface. The student places the block onto the surface as shown in the figure. The student compresses the spring by moving a block distance x to the left as shown in the figure. When the student releases the block, it accelerates across the surface. Friction then causes the block to decelerate and comes to rest as shown in figure 16. Okay, that's fair enough. So what they are going to do is, this is your block. So what they're going to do is they're going to push this backward so that the spring compresses and it stores elastic potential energy. And they said that the surface is rough as well, like the friction is there. Friction then causes the block to decelerate and coming to rest. So what they're going to do is they're going to release it. So they just release it. When they release it, this move forward, but then there is friction over here, and this causes this to decelerate and it eventually stopped over here. So it means that initially it was elastic potential energy, at the point of release it was kinetic energy, and when it was going through this, it stopped, its kinetic energy 0. So all the kinetic energy is gone against work done against friction. It means that all the kinetic energy is gone into thermal or heat energy, it is dissipated. Okay, so what's the question now? The question is, the student makes repeated measurements of D. Okay, like the stopping distance. Table shows the record of D for one particular value of X. X means for one compression. So D is in millimeter. Be careful with that. 79, 82, 81, 79, and 80. And they're saying calculate the percentage uncertainty in the mean value of D. So first you say, what is the mean value, like average value? It can be written by both of these. So average, is sum of readings divided by number of readings. So you have to add all of them together. And then how many of them? Oh no, it's 5. I was about to write 5. I don't know why I wrote 3. So you divide that with 5. So you get your answer. You have to do the calculation. And well, it's coming out to be 80.2, around 80.2. So what you do is, now the percentage uncertainty in D, in the mean value of D. So the percentage uncertainty in mean value of D is absolute uncertainty in D over mean value of D multiplied by 100. So for the absolute uncertainty in D, you will use another method for like delta D. As it is, you will be using range method. As the data is given, repeated data is given. So for that, you use the range method. And what is that? Absolute uncertainty is equal to maximum D minus minimum D divided by 2. So the maximum D from here is 82 and the minimum is what? 79, and you divide it with 2. So this is like 3 over 2, this is 1.5. So what you're going to do is 80, you're going to divide 1.5 with 80.2 and multiply it with 100 to get the answer, right? So your answer is around, we have to look for the calculation, that what is the answer. So it is 1.5 divided by 80.2, so it is 1.87. So your answer is 1.87, or you can write 1.9%. So this is your final answer. Moving forward. Okay, just look upon this graph now. The student determines the mean value of D for a range of values of X, and then he plotted a graph of X square against D. Okay, so now carefully look for the graph that X square is having 10 to the power negative 3. It means all these values of Y-axis is having 10 to the power negative 3 along with it. Be careful with that. And then with D, you have 10 raised to power minus 2. So with every value, 10 raised to power minus 2 is there. So they're saying you that draw the best fit line. Well, the best fit line features, for best fit line, what you have to do is, okay, so for the best fit line, remember that number one, you have to use 20 centimeter ruler with you. You have to take this with your exam, and a D as well. Not necessarily required here, but in the exam, in any question to measuring the angle, you can be in the requirement of using the D. So the second thing is the line should be thin and fine and jointless. That's why I'm recommending 20 centimeter ruler. Third is equal scatter of points. Equal scatter of points. The points should be equally scattered, right? And it's not necessary that you have to start from the origin. If it is going to the origin, then it's fine. I can't draw it like straight, but I will try. Oh, yeah. So it seems to be a little going away from here. It must be going like that. So just forgot about this line. So this is, let's say, your line I have drawn with the free hand. You have to draw it with the ruler. So 1 mark for that. And then they're saying that the frictional forces between the block and is given. Friction is mu W, where mu is a constant, nothing to worry about it. The elastic potential energy is given as E is 1 by 2 kx square. Yeah, this is in the insert sheet as well. But in the insert sheet, this formula is not given. The given formula is energy equals half F into delta L. And then you can say that this F is equal to K delta L. And then you can do 1 by 2 K delta L square. And this delta L can be extension or compression. So that's why you can say it is 1 by 2 K E square or 1 by 2 K X square. Okay. So where K is the spring constant. So show that X square is equal to 2 mu mgd over K. Well, this looks very scary equation over there, but don't worry. Where m is the mass of the block, and this is only 1 mark, so don't worry about that. Okay, so now in the previous question, we have seen that when you compressed the object, it was having elastic potential energy. So elastic, and then when you release it, that was converting into kinetic energy, right? So we can write this. And one more thing, this kinetic energy was work done against friction. This was like friction, drag force, friction into distance. And distance was how much? D. D distance was the stopping distance. So we can now relate these two together to get to the our answer. So we can say elastic potential energy is half kx square, and this is F, and F's value is given over there, which is mu W. So this is mu W into D. And W, at place of W, you can write mg. This is the trick over here, right? And now you have to make x square as the subject. Only keep x square over there and shift the others on the other side. So this is 2 mu mgd over k. So see, we got the answer just by doing one step. We say that the spring's elastic potential energy is converted into kinetic energy, which in turn is converted into work done against friction. And then you just wrote its value, half kx square, and at place of f, we have written mu w, which was written over there, here, and then you simply shift all others to the other side, and you got your answer. Now they're saying determine mu using figure 17, where k is 60 and m is this. So using figure 17, so let's jump back to figure 17. What is figure 17? This is the graph. It means that they are asking us to find the gradient. And gradient is x square over d over here, because this is y over x. So you simply find the gradient. Just take 2 points, whatever, and take their gradient value. So measure the gradient. Gradient is y2 minus y1 over x2 minus x1. Just measure this gradient and you get the value of x square over d. So let's come back over here. And we know that it is x square is equal to 2 mu mgd over k. So as we have to find the value of mu, so just keep mu over there, and this is x square, shift d over here, it will be divided over here, and then shift others as well. So I can write it separately. This is k over 2 mg. So the mu will remain over there. Like I have shifted everything other than mu to the other side. And this one, remember, is the gradient. So I will write that gradient, whatever the gradient is there, into k over 2 mg. And you know the value of k and m from here. So put k value of k and m and gradient, and you will get your answer for mu. I hope you can find that. So its value is in the range of around 0.29 to 0.31. Whatever comes, your answer comes in this range, it is fine. So that was the end of section B. I hope you have learned some important things. The first was the Young modulus and how to deal with the graph. And the second one was related to energy plus how to deal with graph. So I will recommend to practice this section a lot, because this is the section that is having some tricky concepts about graph. So in the next video, I will be focusing on section 3. That will be the MCQ section, and there are 14 MCQs. So just wait for that video, and that will be launching soon. I hope you enjoyed today's session and you must have learned something fruitful today. If yes, then do comment and like the video.